right, yes. So we're live.
Okay.
Good morning, everyone. First time. Let's do a quick check. Can people hear us? And by us, I mean myself and Phil Bell, both. So, I'm waiting on responses. Anyway, how are you, Phil?
I'm well. I'm sort of getting to the period now, so I'll be getting back to making a few videos.
Okay.
It's as you know, so, and I've had more pressing things to think about. So
Yes.
I'll be able to get onto that.
Okay.
Now,
So they say they hear me. Can you hear Phil? Yep. Okay. So they're hearing us loud and clear. Excellent. Excellent.
okay,
So,
all right, that's good. Okay, that's good. So what I wanted to go on from time and have matter.
Yep.
Okay, and have a look at specific examples.
Yes.
And one of the people that has mentioned to some degree, but not all that well, is called de Broglie.
Yes. Yep.
De Broglie in his PhD says that all matter has wavelengths.
Yep.
Has resonance and has waves, and came up with some interesting formulas for that. Which is still applied today, and so I just thought we might just go through a couple of things. Now we spoke about how light is on the magnetic spectrum. Okay.
Yep.
The electromagnetic spectrum. In this first is maybe puts the examples on the board, and then actually solve those examples.
All right.
Right. Start with to say that blue light with a frequency 7 by 10 to the 14 hertz. Okay, so we'll have a look at that. Blue light. Okay. As a frequency, and it's measured at 6.7 by 10 to the 14 hertz. Okay, 6.7 by 10 to the 14 hertz, which is pretty quick as things go. And then we're going to so our first part of to calculate the associated with a bundle of this light.
Okay.
So calculate the energy.
Yep.
Okay. From a bundle of this light. Okay. So that's, by the way, a phrase that's used when we talk about light, and we might call something a bundle of light. Okay. From a bundle of light. Blue light, obviously.
So just before you go much further, I'm getting some feedback that your sound is very choppy and it makes it difficult to understand.
Yeah, I imagine it could be. You know what? Just give us everybody just hold fire. I'm going to try and plug in a Yeti.
Okay.
See if that I really should get a lapel one. You know. That before next time.
I'm not sure if you follow. There's a mathematician called Red Pen, Black Pen, or Black Pen, Red Pen. He has a microphone that looks like a Pokemon that he carries around everywhere when he's doing his lectures. It's quite funny.
Let me see if I can't improve. Worried about that when I turn away from the thing that I would. So just So let's this is probably a good investment. We'll just try.
So yeah, I'm getting some. So I'm hearing you perfectly fine. So your sound is getting to me fine, and some users say that it's getting to them fine. That does sound a lot better.
Okay, so can you still hear me?
Yes, I can hear.
I can't hear you. So let's see if I can't audio setting.
Okay, well, your sound went away again. I can hear you, but you're very, very distant.
Okay.
Yes.
Say something?
Yeah, I can hear you.
And I can hear you now. So is that much better?
How are we doing, chat? Anyway, you carry on, Phil, and we'll see what we can do. Somebody's telling me it's OBS. Some people are telling me it's it's really, really weird. Okay.
Yeah. Okay. Just anyway.
Okay, no problem.
Microphone's sort of right there, so it should be. Okay. So so we're going to calculate the energy from a bundle of this light. Okay. All right. Well, first of all, our formula for that. So E.
Yep.
So H is our good friend Planck. Well, actually, I wish he was a good friend.
Yes.
Actually, I wish I was sitting at the Solway convention with the 50 other smartest people that have ever lived.
Yes. I'd feel
I wish I was number 51.
I'd feel quite out of place. However, yeah.
Yeah. So that most certainly would have been a hair-raising experience to be sitting with those scientists.
Yep.
Of that day.
Yes.
Let's have a look at this. So we're saying that energy is of Planck's constant by this is a pretty simple thing to do. So that's going to be Planck's constant by 10 to the minus 34. Okay, and we're going to have this frequency 6.7 by 6.7 by 10 to the 14 hertz. Okay, so those of you who are interested in maths, a really quick way to start solving, instead of trying to plug all of that into your calculator, is deal with the indices first. Okay, so as you know, if we're going to multiply these two together, then we're going to end up with 10, with 20, aren't we? We're going to subtract 14 from 34, right?
Yep.
Okay, and then after that, you can see that this figure 6.63 and 6.67 are pretty close to 1, aren't they? Yeah, so you'd expect it to be 1 times, 10 to the...
round about that order, yep.
All right, so that's the kind of order that we're expecting. So in fact, this turns out to be 4.4 by 10 to the right.
Mm-hmm.
Okay, 10 to the minus 19 joules. Okay, all right. So we're going to multiply these two together. So you can see 6 sixes are 36, and the rest of the change comes up to 4.4, 44, and then 10, which would be 10 to the minus 20, and then we bring it back to scientific notation where we end up with 4.4 by 10 to the 4 joules. So so let's have a see. What does that actually mean on the board over here? So energy is energy, and ways of expressing energy. So half mv squared, for instance, is one way, and in this case, the frequency times the Planck's constant. So another good question from this is let's see if we can find them that's associated with a quantum of blue. If we can find the momentum. So part 2 for this question. Part 2 is from here. Okay, find the momentum associated with a quantum of blue light. So, okay, find them associated with a quantum of blue light. Now, what's important, I'll come back to this, and the reason that I've chosen this question, it refers back to some of the questions that we've had in the past, and where people have described, the motion of light. So we'll have a little discussion on that question. So here it goes. So the momentum, you got to remember that here we're talking about in classical. So this is stuff the photon, like for instance an electron. An electron is like the size of Earth, all right, compared to the sun. All right, if we're comparing a photon to an electron, okay, so it's massive in that. So in classical physics, where we're even talking about something is on, we're going to say that momentum is equal to the mass times the velocity.
Yep.
If you were with a flat, from a flat Earth point of view, you'd immediately be saying, "Well, what's mass?"
Oh dear. Yes.
You want to this. You want to try and so we're not going to discuss what mass is. I can think, but in any is the Now, this is an important part. If you manage to crash your car into a pole.
I'm not sure that manage is exactly the right word. I think if you've mismanaged your car into a pole.
That's right. Yeah, exactly. So whoever it is, or the insurance company, work out how fast you were going. Okay, and they can certainly. This is the which is another interesting thing about why while the Earth and the Moon keeps going around the Sun. Okay, so conserve, let's say P1, and where P1 ultimately equals MV1 was also going to be equal to MV2. Easy for us to, if we have any one of these variables, and we, the first object, this object doesn't change in its size unless bits of it fling off, because we really did hit the pole hard. In which case we still have to work it out what your velocity is at the end of this after hitting the post. Anyway, physics, but in fact, momentum applies to photons, and in fact, over the speed of light. Determine so we can actually apply because electrons are in this funny zone. also behave like photons.
Yep.
Okay, so they have a wavelength pretty much like photons and behave a lot like photons. So we can equate these two together, although speed of light. So if we have this somewhat less, so let's have a look at this particular example. Calculate this, the 4.4 by 10 to the minus 19. So, okay, so let's work out the moment energy. We worked it out over here. We got 4.4 by 10 to the minus 19 joules. Okay, and then we're going to divide that by the speed of light, 10 to the 8. I think that's sort of close enough to that. Meters per second, and so you can see units for momentum are going to be per meter second.
Yep.
Okay, and in fact, and joules, newtons. So therefore, we have 5 by 10 to the minus 27. 5 by 10 to the minus 27. Okay.
Yep.
In a nutshell, from if it did come, would be, well, you see, the reason putting up the question is because this is actually varies. You know,
yes.
Okay. This is experimental stuff that you can actually. If this is the model, E equals HF, you can actually do this and work out these values with other ways of work. That's how basically science is done. Okay? So we don't. Well, I think this. You know, the Earth moves around the sun. Therefore, we suddenly start believing that.
Yep.
Okay. We'd want to test that, do all sorts of different tests to find out if that was actually true. People don't want to start believing stuff that's patently false.
Yep.
Unless you want to believe that the Earth is flat.
Yep. Well, I mean, it's so. This is the key thing. Like, I noticed after our last episode, there was actually a flat earther in the comment, comments, who was talking about sort of how what we were talking about was not physically verified. And I asked him to explain. I asked him to be specific. What are you specifically referring to that isn't physically verified? That is not demonstrably true. And at that point, he became silent, like he didn't have an answer to that. And it's frustrating because yes, we don't go through every single physics experiment that's ever been done to demonstrate the body of knowledge that we have. But that would be a waste of time. That science has already been done, and the way science works is that we build on it. We demonstrate that it is repeatable, and once it's been demonstrated to be repeatable, we move on. Science moves forward. It doesn't obsess over repeating every single result that's ever been developed in the history of mankind. That's not how science works. It just frustrated me a little bit that somebody would come in and say that sort of thing. So I thought I'd vent.
Yeah, no, fair enough. Then and I go along with that too.
Yeah.
So let's have a look. Let's see if we can explore this a little bit further. Okay, so so if you're writing this down, well, I presume you already have, and if you haven't, you can look at the video again. So I'll just remove it. Okay, at this from a different perspective. What is the energy? And I don't know if Clive is there, but Clive, he can work this out ahead of. Is our friend Clive in?
Yes.
Tony?
Yes, he is. He's in the chat.
Okay. Yeah, this one's for you, Clive. Okay. So, what is the energy of each? Clive could probably do this while he was asleep. Okay. Emitted by a green light, a source of green light. Okay, so that's important. Okay, and this has a wavelength with a wavelength of 515 nanometers. Okay, so just for the purpose of the of people who are lay people who may not deal with things that are nanometers.
Yep.
Let's say, for instance, across here I've got 1 meter. This board is about 1,200 millimeters. So I'll tell you, a meter comes to about here. If that's 200, so about 8 inches in the old language. That's let's call that. It's probably a bit more than 200, about that 200. Okay, then therefore that from here to this other end over here is a meter.
Yep.
Okay, so now what I want to do is I want to break this up into 1,000 pieces. If that's a
Yep.
meter. Okay, so if I break this, I'm going to get a millimeter. So milli. If we 1,000. Okay, 1,000 kilo, but milli 1,000. So 1,000th. Going to get millimeters, and of course if we break that down into meter, which I can't draw, if I can somehow break that down into 1,000 pieces, I'll just get a micro being 6. So that's so now I've broken down this meter. Okay, so I've got a million out of that. So if I'm now going to take each one of these micros and I'm going to break that down into 1,000 pieces more.
Yep.
So as you can see, that would be if I tried to do that. So this is what we're talking about when we're talking about 515 of them. Okay, small stuff. All right, so that will give you some context. Somewhere.
You had it just a little while ago, so
down and even when they're right in front of me, okay, so that's essentially what that means. You can deal with this. Clive have probably got the answer to this by now already, I would imagine. Okay, so where are we? Interesting about question 2. The arguments we have is about the sun. Okay? Earthers say is the sun is really close.
Yep.
Number of problems with that. And that is the amount of energy that we get from it that we can measure. As you can see, we can actually measure the stuff. We can measure the level of energy that we get from it. Okay, we can measure the amount of energy that arrives.
Yep.
So when you look at the amount of energy that arrives at the Earth, and you see the sun, and and is the small thing that they describe it as, you realize that if you do these calculations, put out the energy that would be needed
it is
to arrive at that 10 to the 26 joules that we need on the Earth, that arrives on the Earth.
Well, so the amount of energy that's entering the ocean, we can measure ocean temperature increase. So the oceans are getting warmer as a result of changes in radiative forcing within the atmosphere. The ocean is getting warmer at the rate of 3 Hiroshima atomic bombs per second, which is obviously a huge amount of energy. A small sun can't produce even that amount of energy, and that's only a small amount of the total energy we receive from the sun. It's they don't know the scale of energy that they're talking about. Their ignorance shields them to some extent from having to explain any awkward questions. It's a great point.
Okay, we'll just finish this. Okay, so we're going to talk about a green laser. So this is a legal laser, so 0.3 knot. Mine, which is in the order of watts. So have a look. See this. So we say how many photons per second are emitted by a light source. So we're just talking about a laser now, not the sun. So I want you to think about this with the sun. Okay. So emitted by a 0.3 watt laser, green light. So we'll just say as meters. Okay. -9. That'll do it. Okay.
Yep.
Okay. So what else do we want to? All right. Okay. All right. Well, so this would be equivalent to a 40 watt fluorescent tube, for instance. Okay.
Yep. Clive says it's 3.85 by 10 to the minus 19 joules per photon. All
right. Let's just get rid of him.
Nobody likes a show off, Clive.
Right. Although, shall we argue with his significant figures? Actually, he even got that right.
So let's not argue with his significant figures.
No, probably not. So the energy is equal to Planck's constant, okay, times the speed of light, okay, and we're going to divide that by the wavelength. Okay, now. So the people watching this is a really, really important equation. And I've got to tell you now, think about this. You must not forget this for the rest of your life.
Yes, it's important. So
it's really important. So that you have to remember for the rest of your life. Okay, so here we go. I've said that before, and then 5 minutes later they forgot it. Okay, all right. So let's have a look at that. Okay, so if we did this, we would have got 6.63 10 to the minus 34, and we're multiplying that by 3.0 by 10 to the 8, which is the speed of light. By the way, we didn't pluck that
no.
out of our butts either. Okay, many experiments. Okay, all right. So every Tom, Dick, and Right and does. So that's by experiment. That's come about. So that isn't something that was plucked. Okay, all right. So if you want to get really technical, I think it's about 2.993. It's 2. 2.9979. So you can see that. So the speed of light is certainly known. Actually, if the speed of light wasn't that accurately known, we would have some serious problems.
Yeah, exactly. Yep.
How important that is. That it's really important. Okay, because people would think they over there, and actually they.
Well, I mean the very definition of a meter plays into the speed of light. Like how we define and measure distance. The light is inherent in how we understand the distances between objects. Yeah, Clive Wells says he usually takes C equal to 1 in the appropriate units. It just makes any practical application completely useless. If we had to define the distance from here to the shops in terms of light seconds, it's that would not be very useful. Our signs would have to be a lot larger. Anyway.
Okay, so remember I said that this over here, how many we're doing this first one here, the energy of this green light. So now we know it's 3.86, 19 joules. So you can see this is actually, you can see how small that is. That 10 to the minus 19 is a pretty small number, right? And that just comes from. So we're saying that's the energy from photon. Each one, okay, of which there are trillions and trillions and trillions. So you add them all together, and in fact, look, just from memory, I think it's around about 6, could be about 6 or something like that, by 10 to the 20 watts.
Right.
That comes from the sun. That arrives. The sun does about 10 to the 26 watts, pretty sure, and we get, which is joules per second, and we get about 6.5 by 10 to the 20 of those. Yeah,
I think it's what 20.
Yeah.
2367 watts per square meter, something like that. Something.
Yeah. Okay, so. As if I'm going to stick all of this in my head and try to remember.
Well, I mean that's the thing. Like somebody asked me what the escape velocity what the escape velocity of Earth is, and I said, well, I don't know the number. The formula is a half VE squared equals GM on R. Where m is the mass of Earth, r is the radius that you're at, and ve is the escape velocity. So I can calculate it any time I want, under any conditions I want. But the number is useless because it's not entirely useless, but it's a very limited form of knowledge. It doesn't actually show understanding of the physical phenomenon you've got. Okay.
Okay, good. All right, so the next thing is I'll just get rid of this over here. So I need some space. Okay, so the next really bit of good information that you can have, and you can apply that in all sorts of avenues of your own life. Okay, so the power is equal to the energy that's emitted. Okay, energy that's emitted. Okay, divided by the amount of time. So, change in time. Okay, it's pretty simple. All right, so you can remember that for yourself. Okay, so when you're talking about power, no matter what, we're talking about how long. So, for instance, you put your heater on, and your heater is 2,000 watts. Well, what exactly does that mean? Okay, and basically what that is, it's the amount of energy that your heater consumes. divided by the amount of time that that you're going to leave it on.
Yep.
Okay, so you'll find usually you'll have kilovolts per hour. Okay, so or whatever it is that you're measuring that in. Okay, so let's have a look at this second one, which is really important. We're talking about that that 0.3 watts. Okay,
Yep.
so if that's the case, then we could say, well, if this for one of them, or one of these photons that come from here, then when we could say if we wanted to know how many photons there were, then we could just say that this is the number of photons. We'll just call it n, and we're going to multiply that by the energy from the photon.
Yep.
Okay, and then divided that by the change in time. Okay, so let's see if we can just rearrange our formula. So we've got the number of photons. Okay, this is power, by the way. So now we're going to say that energy, the number of photons, is the power times the change in time. Okay, divided by the energy. Divided by the energy. Okay, and this is important because we'll just discuss that. And of course, probably Clive has this already, I imagine. What a show off. Okay, and this will be probably 8. He'll probably have that and the sig figs, right? 10 to 17 by 10 to the 17. 10 to the 17. Well, just as a number, isn't it? Yeah.
Yeah.
Okay. All right. So this is just as a number of photons.
Yeah, that's just a number. Yep.
Yeah. All right. So power. What would I apply for power? Well, we worked it out before, and then we've got the change in time. Let's say for a second. So we're just saying that's 1 second, and then we divided that by the energy, and that tells us how many photons are arriving. If you went to the beach, all that sand at the beach, you know, your average beach, a few miles long, there wouldn't be that many grains of sand there.
No.
Okay, that's kind of how many photons would be arriving, you know, per second.
Yes.
And wait for it. This 0.3 watt laser, not the sun.
Yes. So it's a you know, it's a you know, the and we can work in terms of individual photons. We can slow we can control the rate at which stuff is emitted and stuff arrives at a receiver, and we can control that. And we do have an understanding of the energy levels involved. You know, how much energy it takes to get the photoelectric effect to work, and indeed we understand where the cutoff is. It's one of the things about that sort of led to acceptance of the quantum theory, was the fact that the photoelectric effect, shining light on a piece of metal, had. Sorry, I'm getting confused here. I'm actually fasting because I've got a blood test later today, so I'm a bit lightheaded.
Okay.
But there's an energy threshold. Below the energy threshold, the effect cuts out, and we understand all of the peripheral details. It's not just the primary column of this phenomenon that we understand. All of the subsidiary questions that we can ask and that we can investigate, we do go and investigate. And it's not a one-dimensional field of knowledge where we just assert an axiom and say, okay, well, let's investigate the axiom. We investigate as many consequences of the axiom as we can. We do a fully three-dimensional investigation of what's going on. Okay.
All right, so that's an excellent point that you've raised there, and it leads on to this next question, which I want to put up, and just so that people can think about this in terms of how useful it is, because if we think about the hydrogen atom having its electrons, having its one electron, if you like. So assume that it's not an ion. If we impart energy into it, okay, then back to its natural state, it's going to release this energy. And it's this releasing of this energy that, and the thing about this is that if we think about energy levels, let's say that's the grand, we've got energy levels, so n equals 3, n equals 2, n equals 1, and so on, or the other way around. It doesn't matter which way you decide to work these out. And so as will climb up to this one, or it could go all the way up here, or it could go all the way up here, and things that are over here could get up to here or there, and so on. Now, as a result of these atom being excited, and then coming back to its normal state, energy's got to be the axiom that energy is neither lost or gained. Then this energy is going to come back as photons. Okay. Now, an important thing. Again, it makes my blood boil, literally, when I hear flat earthers all at 15
yes,
call Einstein an idiot.
Yeah. Okay. Yes, that is true. It is galling. I don't think that they genuinely understand, and this is one of the things that sort of I appreciate. There are you look back at the great figures of science, and even some of the great figures of science today. There are people I work with who I consider to be vastly more intelligent than I am. And you'll see students and you go, whoa, this kid is so bright. I am so old and slow in comparison. And you realize sort of there's a significant gap between me and a really, really bright person. And that's not selling myself short. I'm actually quite arrogant about how bright I am. I don't think I think I'm actually quite intelligent by general standards, but I'm nowhere near the top tier. And I don't think that flat earthers or the general public in particular understand the sheer chasm that exists between their intellectual level and that of the greatest minds on the planet. It is genuinely vast. It is really, really large. And to have people at the very lower end of that spectrum, presuming to comment on some of the greatest intellectual achievements humanity has ever realized, is as you say, thoroughly galling. The Blue Marble Science. Shout out to Blue Marble Science. It is in the chat, and he recently did the as you will know, and as I hope everybody in the community knows, he's been doing a fabulous reconstruction of the Cavendish experiment. Cavendish, if you look at Cavendish's achievements and his career, fabulously intelligent individual. Anyway.
Yeah.
Sorry, just wanted to leap in on that rant. Seemed like a good opportunity.
It's okay. I'll just write this out first, and then I'll read it out, and difficult to read. Okay. convert all of this energy to electricity. So next week, Tony, we'll actually look at electricity in detail and see, well, where does electricity? That might take a couple of these sessions to look properly at electricity and have a look at some of the issues, and also how we can solve. How can we demonstrate that what we know about electricity is in fact, in fact. So we'll have a look at some of the evidence for that. But anyway, so what I'll do is I'll for this particular problem, and this one over here, another one of life. Okay, so this is actually used, this is very, and I've got this used many, certainly used a lot in physics. Remember that E is also equal to half mk, half mv squared, among a whole plethora. Okay, and energy is energy, however you do it. Okay, so now let's have a look at this. So if that's the case, then we're saying that, so we're working out this. Now that the charge of an electron, so the charge of an electron, okay, is 6 by 1.6 by 10 to the minus 19 coulombs. Okay, the minus 19 coulombs, that's the charge of one electron. Okay, at what the voltage of that is. So we already have the energy. I'll rewrite this so that we've got V is going to be equal to, put that on the other side of the equation, the end of it, the charge. Okay, and Clive probably has the answer to this already. All right, and to 1.6 volts. Okay, so let's fix, make it 1.6. Okay, so what is this telling us? Let's go back to some of the to the theory which we described last time. We've got a plate, and we've got photons hitting this plate. As photons hit this plate, they eject. So this is an electron coming here. So this is a photon over there coming in, and as a particular wavelength, okay, that is kind of important. Then it will eject an electron. So let's think about that in terms of your life, because buying solar panels, for instance, okay, and working out, and we've got a good one, or whether you've got, okay, so some of the things you can think about is that how does it work, and whether or not you got ripped off depends on a number of things, and one is the quality of this, and that's really important. So if inferior equipment is used, then effectively you are getting ripped off. Not just this plate, not just this over here, but then how is the how is electricity collected? Okay, so that would be of your thinking when you are purchasing panels. The other thing is that remember that we're collecting these electrons. Okay, and of course the stuff in your house is AC. All right, so alternate current. We'll talk about that next time, about the difference between DC and AC next. So this is a direct current, and then it's going to need to change into alternating current and stuff like that.
Yep.
Okay, so part of the thing, so what you need in between your solar panel and the collector of these electrons, what you need is something called an inverter.
Yep.
Okay, so again, this inverter, and it costs $2,000 or $3,000 just for the inverter, and you think, why is it this just silly? Okay, which just says inverter on the outside costs so much money. This silly box that's in there has to convert your DC current into AC, and it's got to do that in such a little of your energy as possible. So again, its components are because you want to conserve as much of that beautiful sunlight that you spent as possible. Okay. So you don't want that wasted in inferior product. Say half of your energy is because you're not really interested in heating up the world outside. Okay, all right.
Well,
so
I just sort of one of the I just want to mention something. I mentioned it last week, but I'll mention it here as well. We've had a couple of questions about sort of the energy output from the sun. Colin has asked if there's a gravity effect on photons leaving the sun. And Rachie has asked about the entire, are photons leaving the sun continuously? And I just wanted to address those points a little bit since we're on the subject of solar panels. So actually, photons are released from, the energy is created inside the sun as a result of fusion reactions. And actually, your average photon inside the sun bounces around inside the sun for about 10,000 years before it gets to the surface. It keeps on, it'll move a little bit, then it'll get reabsorbed, then it'll get re-emitted. And whenever that happens, it's got a random direction that it goes in. It doesn't just go out. So it may go backwards. So actually, photons take about 10,000 years to get to the surface of the sun, and then they're emitted, and they take about, the photons that we receive take about 8 minutes to get to us after they're emitted from the sun. Now, actually, and what Phil was talking about with the momentum of photons is crucial in keeping the sun operating because it's radiation pressure that prevents complete gravitational collapse of the star. So there's gravitational pressure pulling down on the star, making conditions suitable for fusion to occur, and then there's radiation pressure that keeps the star from collapsing completely, and these two pressures are in opposition, and as the sun begins to run out of fuel to maintain the radiation pressure, gravity will get stronger, So the very existence, the very structure of stars is a demonstration of how radiation pressure works and how fundamental it is to our reality. Would you agree with that, Phil?
Yeah, totally, exactly. That's really well put. So just to finish up on this particular thing, looking at this to determine, as you can see from here, that based on the energy, we're able to what voltage we're likely 6 by 10 to the minus 19 joules. Okay, which as I explained to you was actually quite over there. 6 volts. This is, and the brilliance of Einstein. Okay, that.
Yep.
All right. So you can see if you're getting 1.6 volts from this scenario, imagine like how much energy there is in the sun, for instance. We are that's arriving. It's 1.6 by 10 to the minus 19 producing 1.6 volts. Now imagine this is here is 2.6 by 10 to the 20. So it's right in the opposite direction to the 20. Okay, and now if you try to imagine that and think, well, wow, that is a significant. One of the questions I got with regard to that, I presume that, by the way, all right, okay. One of the questions we got was the sun, for instance, 93 million miles. You know, we'll see them. If they had to come, had to travel 150 million miles, we're talking about kilometers. For instance, if the sun blew up, we wouldn't know for 8 minutes? 8 minutes. We wouldn't know minutes. Okay, so the sun could go off and we would still 8 minutes later.
Yeah.
All right, and then we know it's cooked.
Yeah. Yep.
So how does it get all the way from? Okay, because what they do is they okay, so they say, and that's true. Okay, so let's have a look at an idea about Earth, by the way.
Yes.
Okay. See now how absurd that is. If we're talking about something, let's say a point of light that produces, looking at inverse square, and then of course this is each of those. You need 4. So again, that. So as it's not that the photon is getting smaller or less energy, it's just.
Yes.
So let's say, for instance, this is the little Earth over here. This is the huge sun over there, and there's a little Earth right there. Well, think about the amount that's all over here that's going to miss the Earth.
Yes.
Okay, so when we talk about this photons coming through over here, it's just this little bit over this section here, maybe arrive on the Earth.
Yep.
We can still see that because these photons that square over here, there's nothing in between there and there to stop them.
Yep. It's the just to clarify a little bit here. So the key issue is the solid angle occupied by the Earth from the perspective of the Sun. So there's a if you're at a particular point, there's everywhere. There's 4 pi steradians. Steradians is the unit of solid angle. So there's just the entire surface of the sphere around you. But the Earth from and I'm gesturing like an idiot even though I'm not on camera. But the Earth only occupies a very small solid angle. It's the total solid angle out of that proportion. It's the ratio of Earth's solid angle to the total solid angle of the sphere of Earth's radius. Sorry, just wanted to explain in slightly more technical terms, just in case people want to go and follow this up and sort of look up the terms that we're using or that sort of thing. Anyway, carry on.
Yeah. So just to go over this again, the inverse square law would mean that photons here would diverge.
Yeah.
But there would always be some of the photons over here. So that would diverge even further if the Earth was even further away.
Yep.
But at no point would there be no photons.
Yep.
But the point is that you could look up in the sky and you can see a certain amount of stars.
Mm-hmm.
Well, there's billions and trillions of more stars than you can actually see. Because these photons into your eyes, because at this point over here, you're not capable of picking up one photon and determining that, oh, there's a bit of light.
Yep.
Okay, so that would be extraordinary.
Yes.
So therefore, you need an instrument that does that. So you could put a camera out there and wait for enough of the light to come to you. So if you kept your aperture open and then enough of this light came bouncing in and hit your camera, then you would realize there's a star over there. I can look up there and see the damn thing, but how come it's on the film?
Yes.
And it's not CGI.
There is an implicit assumption that flat earthers make routinely that science has to be part of their personal experience, and humans are the ultimate detection apparatus, and neither of those is true. Spurs on MC Toon's channel the other day was going on, well, if gravity is real, then then you must be able to demonstrate it somehow. Well, yes, I can, but you're suggesting that it can't be done through some experiment. So some experiment in a laboratory, in a man-made laboratory, that doesn't count for some reason. And it's just they construct the most absurd level on which they require science to work. If they get to define science, then sure, modern science isn't what they define as science, but it's a meaningless circular argument. We routinely use more precise apparatus, exactly like film, exactly like telescopes, exactly because they increase our ability to observe and understand stuff, like the inverse square law.
Yeah, so let's have a look at something that is evidence.
Mm-hmm.
So let's say, for instance, we've got a satellite like the Himawari 8. Okay,
Mm-hmm.
So past the silly argument that we can't get anything beyond that this you can't have vacuum next to a. This is how the stupid argument goes. You can't have vacuum. You can't have pressure next to a vacuum. Therefore, you can't have a rocket, therefore you can't have a satellite.
Yep.
This is how their logic goes. Not that about the first thing I said.
Yep. Yes.
Oh no, I'm just automatically right about that.
Yep.
And therefore all the other things fall into place for me.
Yep.
All right, let's more than 3 brain cells so that you accept that satellites are a thing, and then we've got the Himawari 8, which is 36,000 kilometers away from Earth. And it needs to be that, by the way, and it needs to be at the equator. And that's fundamental because Kepler came up with this ratio, which is R cubed over T squared.
Yep.
Okay? And this is a really important ratio because what it's telling us is that at a time, the range, that's the distance center to center for a particular object that's in orbit is inversely proportional to it's the ratio, the inverse of the time that it takes for the object to go around it, the square of the time. So therefore, knowing this ratio, now didn't just pick that from his bum either.
No, certainly not.
Okay, he had lots and lots of observations to work with.
Yes.
Okay, and including those observations were the planets.
Mm-hmm.
And other objects that he could actually see in the star. By the way, you flatties, think about this. If that sun is whirling around the Earth, even if we solve the problem why a round sun produces half a circle, so much to work out how the magic lampshade works, okay, we still have the problem of coming in between the sun.
Yeah.
Sun is close, the bloody planets.
Mm-hmm. Yes, that's it. And sort of, we can get actually radar echoes off the sun, and we can certainly get radar echoes off Venus. And Venus travels between the Earth and the sun, so the sun cannot be any closer than Venus. It just doesn't. It just doesn't work that way. The scale of the solar system is demonstrable. We know how this stuff works, it's one of their housekeeping questions, right? It's one of Nathan Oakley's ridiculous housekeeping questions. Is there any demonstration of how far away the sun is? Well, people have bounced radar off it. Bouncing electromagnetic signals off objects is how we define distance, actually. So why does that not count?
And we have energy, and we have things of that we know
well,
about.
I have a question. So a question about the sun on the flat Earth. So you just went through describing the inverse square law. Okay. So let's suppose that the sun is at 3,000 miles, say. Okay. Above the Earth. That means that it's got a certain intensity just underneath it. But if you move 3,000 miles across to the east or the west or the north or the south, away from the subsolar point, then the intensity of the sun is going to decrease by a factor of 2.
Not bloody much.
Well, no. It'll if the sun is local, then it'll decrease by a factor of 2.
Yeah.
So if the sun is local, then it should be easy to demonstrate this, because you just need to look at it from a few thousand miles away, and you'll be able to see, well, it's only half as bright as it is for the people who are directly underneath it. That clearly isn't the case.
No, exactly. That's a really good point. And I just want to raise that what you just brought up, being this 3,000 miles.
Yeah.
So even if it was obviously one of the things flat earthers don't try to follow things through when they come up with their silly idea. And because I have heard this 3,000 miles many times. Yeah. Okay, so it doesn't matter. It doesn't matter what level you are. The fact is, the distance between, say, the North Pole and 10,000 miles. Okay, or 10,000 miles from the North Pole to Australia. We don't have a model. We don't know. Well, you do know, like we have flights. Aeroplanes fly between Australia and the UK, and the pilots have to work out.
Yep, exactly.
Okay, they need to know how much fuel to put on board if it's a non-stop.
Yes.
Time it's going to take.
Mm-hmm.
And they know how much per per kilometer that they travel. This is not this. I don't. That's hardly even science. It's just arithmetic.
Yeah.
Okay, so we do know how far these places are. Well, if the North Pole to Australia is 10,000 miles, and another country with a similar latitude, maybe say on the opposite side of the world, in South America, say for instance in Chile, is also 10,000 miles.
Yep.
And let's forget about the fact that you could get all the way to Antarctica, which adds another 3,000 miles or so to it. Okay.
Yep.
All right. Let's forget that. Well, obviously we got this distance here. Let's call that Australia. Let's call this the. By the way, for the English people out there, and also and let's call this one over here Chile. Okay. Well, and the sun is miles away. How far does that look? If this over here, from here to here, is 10, that makes that 20, and the sun is only 3. That's this. So if I go 6, 7, that means the sun is just.
Yep.
Did you even think of that, Flatty? Did that even cross your 3?
Yeah.
Multiply that by 10 and see if that still helps you.
It's well, I think if they were, this is one of the aspects that sort of sets an intelligent person aside from a non-intelligent person, and one of the things that I often get unreasonably annoyed by is when I'm talking to somebody who I'm trying to educate, and they say, "No, think about it." I go, well, obviously I have thought about it, and in significantly more detail than you have, because you just said something stupid, but the fact that they said that indicates that they haven't thought about it, but they're not even aware they haven't thought about it. They haven't thought through the simple consequences of their model. They don't explore the logical consequences of what's going on, it's it is intensely frustrating to be that people of such limited intellectual horizons assume that they're one of the greatest intellects to have ever graced the planet. It's confounding that they could even come to that conclusion.
So Tony, the amount of times I've heard that the globe is dead.
Yeah.
That actually use those words.
Yeah.
So let's just have another look at something. So when we look at the sun, which is over there, compared to this, all right, they've got another problem. They talk about the dome now.
Yeah.
Okay, so therefore the dome must look like this.
Yep.
If it's going to be there at all.
Yes, that's right.
Well, if it's 3,000 right over here, try to imagine what it would be over here.
Yes, and
you could probably...
yes, that's exactly right. There's also a matter. There's also a question here of structural integrity. Right? What is this dome made out of? And was it structural integrity? You try building an unsupported arch that extends 12,000 kilometers and see how far you get.
I'd like to.
Because without those. Without those posts, this is the point that I'm getting to. Without those posts, it's supporting itself. You can do a calculation of, I don't care how thin it is. I don't care how how light you want to make it, because your cross-sectional strength is actually dependent on how thick it is. So the thinner you want to make it, the weaker it is. So the less weight it can support. So you've got to, you're making a rod for your own back with this dome suggestion, and there are people who reckon that it's got water on the other side of it. Which compounds the problem. Now it's got to support a significant amount of weight, but be see-through. What are you alleging that this is made out of? What can it be made out of? What physical material has the tensile strength in order to stay in this configuration over tens of thousands of kilometers? The Earth deforms on that sort of scale. The Earth is not, it seems very solid to us when we're walking on it and that sort of stuff. But one of the frustrating things of geodesy is that it's always moving, it's always in motion, it's always deforming. Earth's center of mass is moving as a function of time. It's just they haven't even put in the basic element, like if there is a dome, if there is this container, what is it made out of? Define it for me. What is its tensile strength? Is this physically possible? Team Skeptic says the dome is made from flat Earth tears.
So let's get back to light just for a. We've now established our sun is here and our dome is somewhere above it. That of course they say they don't know, so it could be anywhere. Matter of interest. That's 3,000. So a normal at 3 is just 509 kilometers, and the up would be like down here.
Still well within, most of my work is on the Grace satellites, which are at which have an insertion have an insertion altitude of 500, and then they fall over time. And we still get atmospheric drag effects.
Of course, that's why you have to you need thrusters on.
Exactly. And you look, the atmosphere is very tenuous up there, but it's not non-existent. We're still correcting for it. For the GPS satellites, it does get to the point where that's negligible. Because they're tens of that, 20,000 kilometers away, something like that. I don't understand the mindset of Flurf saying, space starts at 100 kilometers, or there's nothing on, there's a void. No, it's a continuum. Everything's a continuum. Nothing's absolute, and we do very detailed calculations of these for relatively low Earth orbit, and I mean Grace 2 they're thinking of putting in an orbit of 250 kilometers so that they'll get greater spatial resolution. We've got a choice here, and each altitude carries its own challenges. Anyway, sorry, yeah,
that's all right. So just considering that. If we're talking about 3,000 kilometers to 3,000 meters, this idea where there's practically nothing, just at 60 miles, compared to that, is 50 times less of distance. If you think it's 50 times closer, that point at which there's practicals. So even on flat Earth thinking, you could be wondering, well, how does that make even sense? And then you got to think, well, why isn't this sun like a fryer? Because it's enclosed. All of this is enclosed. Where does all this energy go? The sun is putting out energy, and which of course means that this close sun, which is outputting all this energy, which where the hell? Surely it's getting smaller by the day.
Yes, that's right. that is the other. Where is this energy coming from? And I'm sure the more religious flirts will say, well, there's some divine or theistic origin for the energy pouring through the sun. It's some sort of it's at the end of some sort of siphon or pipe or something of divine radiance or something like that. They'll have some idiotic excuse, but yeah, but we can prove. Use it. Last week you talked about spectroscopic evidence. We can prove that the sun consists primarily of helium and hydrogen. Looking at the spectroscopic character of the sun, of the light emerging from the sun, it's got the characteristic absorption bands of these elements in it. And it's producing neutrinos and fusion byproducts. So we can tell what the energy source is. But if it's small, it's got to be using up. I haven't actually done the calculation of how much mass the sun burns on a daily basis. But actually, I should sit down and work out how much that is.
Well, we could just use that calculation because we know how many watts it outputs.
Yep.
So we can transfer that. Remember, E equals mc squared. So we can work that out, and you can work out how much of this is converted to mass, and then you can work out how much mass the sun is losing all the time per second. Now that wouldn't matter if the sun is 150 million miles across.
Yep.
Okay. But it certainly does matter if it's only 3,000. Therefore, it'd be lucky if it's just maybe 50 kilometers across, if that.
Yeah.
So that would be a significant problem because, as you pointed, half of its way.
Yeah.
The sun would be practically non-existent in the 6,000 years since God made it.
Yeah, that's right. It's the sheer unphysical nature of the model they've entombed themselves in is bewildering to me. There's no way in which it makes any physical sense at all. But they seem happy enough. I guess Okay.
All right. So Tony, there's time for us to round up. So why don't we have a look at electricity? Have a look at electricity. Is something that's been known since big. It's just that it wasn't understood, and harnessing it wasn't something that was understood. Obviously, it existed. Lightning isn't something that just came, just 100 years ago, 100, right? So lightning was already there when Faraday was knee high to a grass. Okay.
Yep.
All right. So but nobody actually understood what all of this was.
Yep.
So let's have a look at what electricity actually is, and then come up with some examples like this of deriving stuff from electricity, and let's just point to what the evidence.
Well, I want to make there was a point that I wanted to make. So the governing equations for the generation of light are Maxwell's equations, and they're quite interesting when applied to the motion to electrical fields, because it turns out that we'll discuss this in a bit more detail. It turns out that getting electricity to flow down a wire actually involves waves that extend very far outside the wire, like tens of meters outside the wire. The electrical waves guiding that current through the wire extend either side, and it's a really weird like relativity, like quantum mechanics. Once you start and I think that actually Maxwell's equations were the jumping off point for people realizing, well, hang on, if these things are right, then we need to reconsider how we view the universe. I kind of think that Maxwell is an unsung hero to some extent.
Oh, definitely.
because I think his name deserves to be up there with Einstein, if I'm being honest. But he came up with this mathematical formulation, and Clive's just dropped it in the chat. Maxwell did not have the convenient notation that Clive just used. He had to do it all longhand, but he and he just revolutionized our understanding. And it you just think, when you think of electricity going along a wire, you basically think of it as like a fluid just moving along a pipe. But it's actually much more complicated than that. The reality is much more profound. So I think that's going to be a really exciting thing to turn about. Talk about.
Can I leave that presentation up to you?
Yep.
I'll have a look at the history and for instance the momentums and stuff like that.
Okay.
Electric fields and then we can this idea about the difference between flowing electricity and static electricity.
Yep.
And stuff like that, so people get a general idea about electricity.
Okay.
And then from there we can then extend that to magnetism.
All right. Absolutely.
Okay.
And if anybody's got any questions, please leave it in the comments.
Yeah, absolutely.
Okay.
Yeah. Okay.
All right.
Okay. Thank you very much.
Thank you.
And thanks everybody for
coming.
Yes,
thank you all. Thank you for a wonderful stream. Hope you all enjoyed it. We'll see you all next week.
Okay. All right.
Cheers.